In this video, we are going to see singularities or a singular point of a function f of z and types of singularities. Okay, before that, let us see what is a singular point of a function f of z. A function f of z which is fails to be analytic, at a particular point z equal to a, then z equal to a is said to be or called singular point of the function f of z. So let us see, there are few types of singularities. There are few types of singularities. The first one is removable singularity. Removable singularity. It means that the singular point can be removed from the function. That means the limit exists. In another word, we can say. The second one is a pole, a finite number of negative powers. Then the third one is essential singularity. And isolated singularity. Let us see one by one the types of singularities. The first one, isolated singularity. Isolated singularity. It has a meaning itself of the definition. There is no other singularity. There is no other singularity of f of z in its smaller neighborhood. And next one is removable singularity. Removable singularity. The another type, the singular point. The singular point z equal to a is called removable singularity. Or removable singular point if the limit over the point z approaches to a, f of z exists. That means the limit exists for the given function, then the type of singularity is called a removable singularity. And another type is a pole. Before seeing, pole. So if we can find a positive number or a positive integer such that limit over z tends to a, z minus a raised to the power n into f of z not equal to 0, then z equal to a is called a pole. It means that when we taking the limit for this function, when z approaches to a minus a is equal to 0, then 0 into anything is equal to 0. But this is not equal to 0. This means that the f of z must contain a function in the denominator to cancel this z minus a. Say for example, put n is equal to 1 and z equal to a. I mean the limit z tends to a. So limit z tends to a, so z minus a into f of z not equal to 0. Therefore, the function f of z may be, and it contains the denominator of z minus a. So z minus a plus some functions z square or some constant will like this. Then when we substitute here, limit z tends to a, z minus a into 1 by z minus a plus z square into z minus a, then this and this get cancelled. So next one is essential singularity. If the principal part of Lorentz series, the Lorentz series is nothing but f of z is equal to summation over n is equal to 0 to infinity an z minus a raised to the power n plus summation over n is equal to 1 to infinity bn z minus a raised to the power minus n. Possess, here this is called a regular part and this is called a principal part. Possesses infinite number of terms. The principal part of Lorentz series, this is the principal part, possesses infinite number of terms. Then z equal to a is called an essential singularity. Essential singularity. In short, we can say if there is infinite number of denominator terms, or that is infinite number of negative powers in any function f of z, then that is called infinite number of negative powers. If a function f of z possesses infinite number of negative powers, is called a essential singularity. If a function contains only finite number of negative powers, then it is called a pole. Let us see some examples. Classify the singularity of the following. The first one, f of z equal to 3z divided by z minus 1 the whole square, z plus 2 the whole square or the whole cube into z minus 4. So this function has pole at z equal to 1 and z equal to minus 2 and z equal to 4. When I take z equal to 1, the denominator becomes 0. Therefore, at the point z equal to 1, this function fails to be analytic. And if I put z equal to minus 2 and plus 2 get cancelled, 0, 0 into anything is 0, then anything by 0 is infinity. Therefore, the given function f of z is not analytic at the point z equal to minus 2. And z equal to 4, if I put z equal to 4 here in the place of z, if I substitute z equal to 4, then this becomes 0, anything by 0 is infinity. Therefore, the given function f of z is not analytic. That means it fails to be analytic. And I have only a finite number of terms. Z equal to 1 is a pole of order 2. It represents the number. And z equal to minus 2 is a pole of order 3. And z equal to 4 is of order 1, pole of order 1, or it's a simple pole. A pole of order 1 is called a simple pole. And all these points all are isolated singularities. The reason is that I can draw a smallest circle which contains only this singular point, no other singular point other than this. And also I can draw a smallest circle around this circle which contains no other singularity other than z minus 2. And also at the point z equal to 4, I can draw a smallest circle as much as possible which contains no other singularities other than 4. So therefore I can say that this is the only singularity. So all are the isolated singularities. In their smallest neighborhood is it equal to 1. So next example, the second one is 1 divided by z minus 2 the whole cube, which means that the function f of z is not analytic at the point z equal to 2, because this become infinity when the limit z approaches to 2. Therefore z equal to 2 is a singular point, and it contains only one negative power. Taking this term to numerator, it contains only one negative power. Therefore I am having only a finite number of negative power. Therefore z equal to 2 is a simple pole. Wrong. Z equal to 2 is a pole of order 3. I left to the reader that this is isolated singularity or not. I left to the reader to check whether this function is isolated singularity or not. The next problem, check whether f of z has a singular point or not. Sin z divided by z at the point z equal to 0. Obviously this function is not analytic at the point z equal to 0, but when we taking the limit z approaches to 0, f of z is equal to limit over z tends to 0, sin z divided by z is equal to sine of 0 divided by 0 is equal to 0 by 0 indeterminate form. By using L'Hopital rule, limit over z tends to 0, differentiation of the numerator is cos z, differentiation of denominator is 1. Now taking the limit, cos of 0 is 1. So limit exists, therefore the given function f of z equal to sin z divided by z has a removable singularity, and also one more proof I can give that f of z is equal to 1 by z, and sin z can be written as z minus z power 3 by 3 factorial plus z power 5 by 5 factorial plus up to etc. So when we multiply 1 by z inside this sine function, so z divided by z minus z cube by 3 factorial into 1 by z plus z power 5 by 5 factorial into 1 by z plus etc. So this and this get cancelled. The remaining one will be 1 minus z power 2 divided by 3 factorial plus z power 4 by 5 factorial minus etc. So now taking a limit where z tends to 0 on both the sides, so 1 minus 0 is equal to 1. This is the limiting value. And also I don't get no negative powers in this series, all are the positive powers. Therefore this function does not have finite number of negative powers or infinite number of negative powers. Actually this series has no negative powers, only positive power. Therefore this series cannot be a this series is analytic.